Hello everyone, welcome to today's webinar. I'm Alexandra Taylor, contributing editor for CNEN, and I will be moderating today's event. This webinar is titled, Well, Ain't That Swell? Characterizing Microgel Polymers and Nanostructures by Light Scattering, and is being sponsored by Wyatt Technology. CNEN works with sponsors to identify topics of interest and value to CNEN's audience and consistent with CNEN's mission to provide news and analysis of the chemistry enterprise in a timely, accurate, and balanced fashion. During the webinar, you can adjust the size of the slides on your screen by grabbing the lower right corner with your mouse. If you need technical assistance, please look at the Help widget at the bottom of the screen or type your query into the Q&A box. If you're disconnected during the webcast, please log in again according to the instructions you received earlier. You're encouraged to contribute to the success of this webinar by asking questions at any time during the presentation through the Q&A box on your screen. The questions will be answered at the end of the presentation, and as your moderator, I will be posing as many questions as time permits. Please note that CNEN does not endorse any company, products, or services that may be mentioned in the webinars, and that each webinar will be archived at CNN Online after the live webcast. The presentation today is being sponsored by Wyatt Technology. Wyatt Technology markets itself as a leader in light scattering instrumentation and software for determining absolute molar mass, size, conformation, charge, and interactions of macromolecules and nanoparticles in solution. During the presentation, we will hear from Dr. Mark Spears, who is the Southeast Regional Manager and Application Scientist for Wyatt Technology. I'll now hand over to Mark.
Well, thank you, Alexandra. It's a real privilege to present this material today, and I want to thank everyone for tuning in. And as Alexandra mentioned, the topic of today is characterizing nanostructures by light scattering. And it may be a little bit different from a typical webinar that you've heard on our website, because I'm going to talk about light scattering instruments and techniques in the context of some graduate work that I did at Georgia Tech. Hopefully we can use data that was collected during my graduate research to illustrate the powerful techniques that we have with light scattering. And we'll get to the materials and a little bit more background on that work in just a few minutes. But I want to first start by talking about the challenges of characterizing nanoparticles. Historically, they've been very difficult to analyze. And there are multiple challenges. I've listed just a few here, such as measuring accurate size distributions, characterizing nanoparticle responses to environmental factors, and oftentimes those responses are quite subtle. So having the sensitivity to measure small changes in particle size or some other kind of response is very tough. And traditional analytical tools that we may have in our laboratories have trouble coping with not only the length scales of nanomaterials, but the huge variety of chemistries now represented in the field. But what I hope to show you today is that light scattering and the suite of tools offered by Wyatt Technology is actually quite powerful in allowing investigation into nanoparticle properties, such as molecular weight and radius, hydrodynamic radius, charge, and even size distributions. There are three basic types of light scattering. The first is static light scattering. The second is dynamic light scattering. And the third is phase analysis light scattering. We won't have time, unfortunately, to discuss the last one on the list, but we will talk about the first two today. So let's start by focusing in on dynamic light scattering, or DLS. DLS works by measuring the diffusion of molecules in their solution, and then from that diffusion, we are able to calculate a hydrodynamic radius, commonly abbreviated as R sub H. And how does this measurement work? Well, if we imagine two particles floating around and diffusing due to Brownian motion, when laser light hits these particles, it scatters and then reaches the detector. If the waves, if the light reaching the detector, if those waves are in phase, we get constructive interference, and this results in a very bright spot on the detector. However, at some small time later, as these particles have diffused due to Brownian motion, the waves are now destructively interfering and are out of phase, resulting in a dark spot on the detector. We measure the very fast fluctuations in dark and light spots, and then we calculate a size from these data. And there's, of course, much more to learn about how DLS works. And so if you have questions, please contact us afterwards for a more detailed explanation. DLS is commonly used for particle sizing, and you can get data that looks something like this, where here we've plotted the percent intensity of scattered light versus the radius of the nanoparticle, and you can clearly see the average values and distributions, and we can even tell you in some cases when multiple populations are present in a sample. This measurement takes a matter of seconds and is very user-friendly. So I'll mention two of our dynamic light scattering instruments here. The first is the Dyna Pro Plate Reader 2. It utilizes industry standard well plates, and the measurement of particle size is made directly in the well plate with no sample transfer. The instrument is very, very sensitive, and you can use as little as 4 microliters of sample inside of the well plate. Of course, we have temperature control, and we also have a long laser wavelength in this instrument. The other dynamic light scattering instrument that I'll mention is our Dyna Pro Nanostar. This instrument is a cuvette-based DLS, and it has a very large size range from about 0.25 nanometers up to, and actually more than this slide says, up to several microns in diameter. This instrument is particularly special because it has a built-in static light scattering detector and is extremely sensitive. Not only that, we can use as little as 1 microliter of sample. We can also control temperature with a very wide range, and we have a 660 nanometer laser inside of this instrument. And this is the instrument that almost all of the data that I'll be presenting today in the DLS section of the talk was collected with. Okay, so now let's dig into the samples themselves. So we're going to talk about microgels, and I'm focusing on microgels for a couple reasons. First, as I mentioned, it was work done in my graduate lab, so I really enjoy the topic. But secondly, microgels have some really interesting properties that can only be characterized by light scattering. As we go through the remaining slides, we'll see that microgels have some very interesting responses to their environmental factors, and light scattering is the perfect tool to characterize these responses. But before we can understand what a microgel is, we need to first understand more generally what is a gel. And of course, you're probably familiar with the idea of gels because you encounter them in everyday life. They show up in our food, they show up in different comfort items, and they even show up in medical devices such as soft contact lenses. But what more specifically, and what is the structure and chemical nature of a gel that makes it so special? Well, a gel is defined as a colloidal or polymer network that is expanded throughout its entire volume by a solvent or by a liquid. And that really can be anything, except when the liquid is water, we call it a hydrogel. And characteristically, hydrogels are held together at many different cross-link points by either physical or chemical, physical entanglement, I should say, or chemical bonds. And in theory, if you were to break these cross-link points, the gel could then fall apart and completely degrade. Many characteristics of hydrogels have been studied. I've listed a few on the right side here, But most importantly for this talk, we'll focus in on the last characteristic, which is they can be stimuli responsive. That is, they respond in some way to their external environment. All right, so if we zoom in on the gel and zoom into the microscopic level, of course, that is a microgel. And microgels come in a huge variety of sizes, from tens of nanometers up to about 4 microns, or sometimes even larger. They are spherical polymer particles. And I put an AFM image on the right side here so you can get an idea of what these microgels look like when they're on a glass slide. Each one of the little dots represents an individual microgel. And you can see that the polydispersity is actually quite low, which is amazing considering that the synthesis of microgels is so simple. We simply mix together our desired monomers, heat the reaction up to 70 degrees or so. We initiate with a free radical and then let the reaction proceed for several hours. And a typical microgel composition includes what you see in the chemical structure on the left. It includes NiPAM, which is N-isopropyl acrylamide, as the primary monomer. It includes a cross-linker, such as bis-acrylamide, and oftentimes includes a charged monomer, such as acrylic acid. Now, one of the neat aspects of microgels is even though they're very, very small, they maintain the similar properties to their macroscopic counterparts, except everything occurs on a much faster time scale simply because of the dimensions of the microgel. And the synthesis is extremely versatile, not only in terms of the chemical composition, but in terms of the structural varieties that can be achieved. Our group has made all of these different structural varieties, from a core with a shell on top to multiple shells, even hollow microgels, floating cores, and erodible particles. We can even decorate the surface with some kind of tag or ligand to add functionality to the microgel. Okay, so the first example we see of how a microgel responds to its external environment is the response to temperature. At room temperature, the acrylamide chains in the microgel are hydrophilic and form hydrogen bonds with surrounding water. In fact, many microgels are 90+% water by volume. It's really incredible. And as you increase the temperature, there's a critical point at which the thermodynamics change inside the particle so that the chains now become hydrophobic. That is, the chain-chain interaction now dominates inside the particle, and water actually gets expelled from the interior. And this process can result in a dramatic change both in size and volume. And furthermore, the process is completely reversible. You can switch back and forth between the hydrophilic and hydrophobic states all day long, and you can swell and deswell the particle all day long with no kind of lasting effect on the microgels. And dynamic light scattering is actually the perfect tool to characterize this kind of response. We can measure the size at room temperature, which you can see on the left-hand side of this graph. At 25 degrees Celsius, the radius we measure is somewhere around 200 nanometers. But as you begin to increase the temperature and take measurements along the way, you can see that the particle radius just collapses down to about half the size, 100 nanometers, and there is an inflection point where the size collapse happens very, very quickly. And this inflection point has a name called the lower critical solution temperature, or LCST for short. And this LCST value is characteristic of the polymer being studied. And in fact, it can shift around based on the polymer. Now, with decreasing particle size, we're actually seeing an increase in turbidity. And if you think about that, it's kind of counterintuitive. If something is getting smaller, typically it scatters less light. But you can understand this process when you realize that the particles at room temperature are so highly swollen in solvent that the refractive index inside of the particle is actually very, very similar to the surrounding pure solvent. However, when you cross over the temperature threshold, solvent gets expelled from the particle, and so now the particle refractive index relative to the surrounding solvent is very different, and thus the particle scatters much more light. And you can see from the picture on the right, we go from a clear solution to a very cloudy and milky type of solution at high temperature. So DLS is the perfect tool to characterize something like a response to temperature for various nanoparticles. And of course, this kind of experiment can be done for all kinds of nanoparticles. And I do want to mention before I leave this slide that oftentimes this kind of experiment where we ramp temperature and take measurements along the way is used by protein chemists to study aggregation points or melting points of their sample. So it's a widely applicable technique. I mentioned that the LCST value does shift around depending on the polymer being studied. The LCST for NiPAM, which we've already mentioned, is around 31 degrees Celsius. However, if we change the polymer and use something called NiPMAM, which is a very close cousin to NiPAM, the only difference is there's an extra methyl group on the main carbon chain. The LCST all of a sudden shifts up to 40 degrees Celsius. And it turns out that if you synthesize particles with varying ratios of these two different polymer compositions, then the LCST shifts according to the ratio. And here I'm plotting scattering intensity, so the graph looks a little bit different. But the scattering intensity carries a lot of information as well as the reported size from the instrument. So some people actually consider dynamic light scattering as a qualitative measurement, but in fact it's quite quantitative and data rich. Okay, so dynamic light scattering is great for measuring size in response to temperature, but what other kinds of things can the DLS, or what other kinds of things affect the DLS measurement? Well, anything that affects diffusion is going to affect the measurement since it comes directly from measuring the diffusion of the particle. Of course, small particles move faster than large ones, and if the particle is aspherical or carries with it associated solvent molecules, that's going to affect its diffusion. There are also extrinsic factors, such as the viscosity of the surrounding solvent, and of course the temperature, which also affects the viscosity of the solvent. And it turns out for microgels, there are some other factors to consider. There's the effect of pH. So remember that we have a charged monomer inside of the microgel. So we can play with the pH of the surrounding solution to achieve varying degrees of deprotonation of the acrylic acid group. The more acid groups are deprotonated, the more charge-charge repulsion takes place inside the microgel, and the larger the size of the microgel is reported. This LCST also shifts to higher and higher temperatures with increasing pH. And at some point, the charge repulsion inside the microgel is so great because of the deprotonated acid groups that increasing the temperature no longer has an effect. The LCST is almost completely gone. The other factor to consider with microgels is the ionic strength of the buffer. With higher ionic strength comes more charge screening inside of the microgel, and therefore the reported size is smaller. And you can see here as we increase ionic strength going from the black circles down to the green squares in the graph, that the reported size is smaller, whereas the LCST remains approximately constant. So I want to emphasize the point here that dynamic light scattering is not only the perfect tool for characterizing responses to environmental factors, but it's also an ideal tool for characterizing or rather figuring out exactly what buffer conditions or solvent conditions work well for your sample. My last dynamic light scattering example is for core shell microgels. And we start out with a relatively stiff core, and then we add some kind of a soft shell to that microgel core. And you can see in the open circles in the graph, we start out around 100 nanometers with just the core. And then our shell adds about 40 nanometers to the particle size. And so we can clearly see the change in particle size. And in fact, 40 nanometers is extremely easy to pick up. I've seen changes as small as a few nanometers, and the dynamic light scattering instrument can detect those kinds of changes. And again, I put an AFM image on the right side here because I think it just turned out so beautifully, where you can see the stiff core and then the surrounding shell that is kind of flattened onto the glass slide for AFM analysis. So the DLS instrument can detect small changes in particle sizes and responses. Okay, so that pretty much covers dynamic light scattering. So now let's shift our focus to static light scattering. With static light scattering, we can measure molar mass. We can also measure RMS radius, also known as radius of gyration, or R sub t, and a third type of measurement called the second virial coefficient, which is a measure of how likely your sample is to interact with itself. We won't be able to touch on A2 at all in the rest of the talk, but we will talk about molar mass and RMS radius, or RG. There are two basic principles. Briefly, we'll dive into the theory for just a second here. Principle number one, the amount of light scattered at 0 degrees is directly proportional to the product of the molar mass, the concentration, and the square of the refractive index increment. The equation is here. So we're measuring the intensity of scattered light. We're measuring the concentration. We know D and DC for a particular sample. And so then we can calculate molar mass when all of these other things are measured or known. And this is an absolute measurement. And by that I mean it does not depend on any kind of reference to an external calibration standard or external calibration curve. All of the components that are going into this measurement are measured from first principles. So this really eliminates a lot of problems that can occur if your calibration standards are not similar to your sample. And in fact, for nanoparticles, that's pretty much always the case because there are very, very few nanoparticle standards that would match your the nanoparticle that you are trying to measure. Okay, basic principle number two, the variation of scattered light with scattering angle is proportional to the average size of the scattering molecules. If our molecule is less than 10 nanometers, it scatters light equally in all directions around the flow cell. However, as our particle gets larger and larger, the shape of the scattering intensity begins to get distorted. And so with really large molecules, they scatter light much more strongly in the forward direction than they do in the backward direction. And so we measure how the intensity varies with angle around the flow cell, and then we can tell you what RG is. Now, I haven't really defined RG yet, and so you may be asking yourself the question, what is RG exactly, and how is that different from the sizes that we were measuring in the dynamic light scattering portion of the talk? So let's look at that really quickly. In dynamic light scattering, we get RH, or our hydrodynamic radius, which is the radius of a sphere that diffuses at the same rate as our sample. Contrast that with Rg, which comes from static light scattering, and it's defined as the average distribution of mass around the center of the particle. So fundamentally, these are two different types of radius measurements. However, there's actually a lot of meaningful information if we look at the ratio of the two different measurements. So if we look at Rg divided by Rh, if we get a value of around 0.77, we know that we have a solid sphere. If we get a value that's greater than 1, such as in this case, we're looking at a star polymer, we know that we have a molecule with some kind of extended conformation. So it's important to know both pieces of information to fully characterize your particle. Okay, what instruments are we using for static light scattering measurements? Well, I'll first talk about our multi-angle light scattering detector, which is called the DHEA. And this instrument is capable of measuring light scattering at 18 different angles and can measure up to 1 gigadalton of molar mass, and molecular sizes up to 500 nanometers in radius, or 1 micron total diameter. There's so much we could say about the DHEA, but this instrument is commonly known as the MALS, and it's commonly combined with our refractive index detector, which we're probably all familiar with. The Wyatt refractive index detector, importantly, uses the same wavelength as the Helios, which allows us to calculate molar masses accurately. And these two detectors are commonly hooked up to a chromatography system, but there's a really big problem with nanoparticles. You can't push them through a column. They just get filtered right out of the solution. And so traditional chromatography is not appropriate for analyzing size distributions of larger nanoparticles. So we need to employ an alternative separation technique called field flow fractionation, which can handle a huge size range from the nanometer, around 1 nanometer up to 10 microns or so. And this instrument can be combined with any downstream detectors, such as MALS and RI, and it consists of a flow control module, which is in the top image on the left side of your screen, and also a separation channel, which is in the bottom image on your screen. And the separation channel is really where the fractionation takes place. I'll just briefly explain what's happening. We flow solvent not only down through the channel, but we flow solvent directly out downstream to the detectors. So we introduce our sample, and the cross flow pushes it down against a semi-permeable membrane at the bottom of the channel. When we then remove the cross flow, small molecules diffuse away from the membrane into a part of the channel that has a faster flow. So small molecules elute first, and then they are followed by large molecules. And this order of separation is the exact opposite of what we typically experience with a column. So using this combination of field flow fractionation with multi-angle light scattering, we can look at microgel size distributions. You can see here that we're measuring the radius over some period of time, from about 25 minutes to maybe 31, 32 minutes, something like that. And our size goes from about 65 nanometers up to a little more than 75 nanometers. And I really want to emphasize the point that FFF can provide very, very fine resolution for nanoparticle separations. In fact, this fractionation that you see here is occurring over the span of a little more than 5 minutes. So it would be possible to collect fractions of the sample that's eluting at different time points and have a very, very pure and and low polydispersity solution of your nanoparticle. And of course, this type of analysis can be done for not only microgels, but any kind of nanoparticle that you can imagine, very commonly used for liposomes as well. Okay, so we have the suite of light scattering tools in place now to fully characterize microgels. And so the story I want to tell you to illustrate the power of this type of setup is degradable microgels. And our group made two different types of degradable microgel chemistries. In the first case, we made microgels with a crosslinker called DMHA. And I won't attempt to say the name here, but this crosslinker is cleaved in the presence, or rather when incubated at neutral pH. The other crosslinker called DHEA is cleaved in the presence of periodate. Okay, so let's take these in order. We'll first focus on the DMHA. If we incubate microgels with this crosslinker at neutral pH for some period of time, and then we inject a part of that sample into our FFF mols system, you can see that over time, the intensity of scattered light is decreasing quite rapidly. And this is an indication that the microgels are breaking apart and losing molar mass. Now, I'm not showing it here, but we collected the same series of experiments at a lower temperature, and the drop-off is not quite as dramatic as you see here, but you do still see a decrease in scattered light intensity, indicating that the particles are eroding and breaking up into smaller pieces. All of the cross-link points inside of the microgel are breaking and leading to this erosion. And indeed, if we plot the molar mass over time for this experiment, you can see that there is a pretty dramatic decrease, and it goes out to at least 120 hours. Now, we kept those microgels in solution for 2 months, actually. And if you look at their molar mass after 2 months, it's essentially the same as at the 120-hour mark in this graph. And that should make us ask the question, why is the microgel not completely breaking up into small linear chains? Shouldn't it completely fall apart and be completely degraded? Well, it turns out that there's a little side reaction occurring during the synthesis that's creating cross-link points which are not affected by pH changes. And we'll revisit this in the next part as we talk about the periodate cleaved cross-linker, because it shows up there again as well. Now, interestingly, a decrease in molar mass corresponds with an increase in the particle size. This is definitely a counterintuitive result. But if we realize that the cross-link points within the microgel are being broken, then the microgel is actually free to decompress and swell even further in solution. And so that explains what we are seeing as the microgel size increases over the analysis time. And I just had to put these images in. I think it's such a beautiful example of using the atomic force microscope to track particle degradation. Whether we take the image in the dry state or we take the image in the wet state in PBS, in both cases you can see that the particle is eroding over time and losing most of its molar mass. Okay, so we tried one other degradable cross-linking strategy as well. This time the microgels were synthesized with DHEA. As I say, it's cleaved in the presence of periodate. And we made two different types of microgels with this cross-linker. we made NIPMAM and we made NIPAM. And if you remember from the previous slide, the only difference between these two is an extra methyl group. And that methyl group is present for NIPMAM, which is the particle on the left side of your screen. And the multi-angle light scattering instrument really allows us to do a full comparison of these two molecules. If we look at the RMS radius, it's actually very, very similar, 175 versus 167, indicating that the average distribution of mass between these two different types of microgels is very similar. And that is illustrated by the red dotted line in the images. However, if we look at the hydrodynamic radius, it's very, very different, 225 versus 263. So the NIPAM particle on the right side is much larger than the NIPMAM particle. And in fact, it's really interesting when you start to look at the molecular weight of the two particles. The NIPAM particle, even though it is larger, has a lower overall molecular weight. So really the main difference between these particles is the density. NIPMAM tends to have a much higher density particle than does NIPAM, and we'll get to the reasons that are involved that can account for these differences in density in some future slides. So again, testing for the erosion of these particles was done a little bit differently. We used an instrument that Wyatt makes called the Calypso, and inside of this instrument there are computer-controlled syringe pumps, degassers, and also solvent reservoirs. And so this allowed us to mix microgel and periodate solutions in very defined amounts. And as these solutions pass through the mixer and then downstream into the moles and RI, we can make measurements over time. And with this setup, we can work under constant flow, or we can then stop the flow and measure what's happening. And so, in fact, that's what we did. So if you look at this graph, during the first 2 or 3 minutes, we are under constant flow, and that corresponds to the small flat portion of the curve right on the left side of the graph. Then we stop flow, and all we do is we let the solution sit inside of the flow cell in the multi-angle light scattering instrument. And we monitor what's happening with the reaction. And you can see in the blue curve that, in fact, there's a pretty sharp decrease in molar mass right off the bat. And then after about 5 minutes, we start to see this very linear decay in the particle molar mass, which keeps going out to at least 40 minutes and then beyond. It turns out that the particle loses approximately 2 to 3 orders of magnitude in molar mass after about 80 minutes. I'm not showing those data here, but there's a simultaneous increase in size initially. This corresponds to what we already saw on the previous slide, that the particle is actually free to swell further as crosslink points are being broken. And when we look at take all of these data into consideration, it actually indicates that we have a microgel which is very homogeneous, not only in terms of polymer distribution, but in terms of crosslink distribution throughout the particle. And so we get uniform degradation throughout the particle, and it completely breaks down into small chains. Now, again, these were NIPMAM particles, so this is the polymer with the extra methyl group. However, the situation changes pretty dramatically when we move to the NIPAM particle. And I'll put the two graphs side by side on the next slide so you can directly compare. But here we see both a decrease in molar mass and size simultaneously. And so this is actually an indication that the particle is degrading from the periphery and moving in toward the core. And it's definitely a non-linear type of degradation as compared to the other NIPMAM particle. And interestingly, I'm showing out to 40 minutes here, but after 80 minutes, we do still see that the particle has some angular dependent scattering, indicating that there's kind of a core small part of the particle that just will not break up. And I mentioned that I would come back to this issue. There's a side chain transfer reaction that's happening during the synthesis of NiPAM particles. And it's actually forming these cross-linkers that do not degrade in the presence of periodate. And so NiPAM particles will form these side chain reactions. NiPMAM particles are prevented from forming those because of the extra methyl group. Okay, so let's put these two side by side. You can clearly see the linear versus nonlinear pathways and the very different size behavior between the two types of microgels. We could also ask, okay, so what is contributing so strongly to these microgels having different structures? Because one is homogeneous, one is very heterogeneous. Well, there are actually two factors that are contributing here. The first is the incorporation rate of each type of polymer into the particle. NiPMAM incorporates much more slowly than does NiPAM. And the other factor is the rate of incorporation of the cross-linker into the particle. So these two factors combined mean that we end up having a very different network structure between the two particles. And really, I want to emphasize again that multi-angle light scattering and the systems that we use here, the light scattering systems, are extremely powerful, not only in comparing the two particles, but in actually giving us insight into the network structure and connectivity of these microgels. So light scattering really allows us to dig down deep into what's happening with our nanoparticles. And on our last slide here, we'll think about the reaction rates that are occurring. And so for NiPMAM particles that degrade in the presence of periodate, as you might expect, if we increase the presence of periodate, the reaction occurs much more quickly. And so we can see that by comparing reaction rates inside of the MALS flow cell. And so MALS, in addition to giving us information about the network connectivity, can give us some insight into reaction rates as well. So to summarize what we've covered today, we've seen some really interesting properties of microgels in terms of their temperature responsiveness, the diversity of architectures and chemistries involved, and these responses really make them useful in a wide variety of applications. And light scattering is the perfect tool for characterizing these properties, size distributions, molecular weights, structural changes that can occur, and even tracking degradation of the particles. And FFF MALS is able to fractionate the microgels or other types of nanoparticles, so we can get a really full characterization and separation of those molecules. If you'd like more resources about anything we've talked about today, please feel free to check out our website. We have an abundance of application notes, white papers, other webinars similar to what you've heard today. We have an extensive bibliography, over 11,000 publications now using Wyatt instruments, an extensive light scattering theory section, and of course you're always free to get in touch. Just email us at info@wyatt.com, and I put my email as well, mspheres@wyatt.com. We always love to hear from you, get your thoughts, and talk a little more with you about light scattering instrumentation. Before finishing up, I do want to acknowledge my former group members at Georgia Tech, particularly Dr. Michael Smith in the left-hand column, who did a large part of the FFF MALS work that was represented in this talk, and of course my advisor, Dr. Andrew Lyon, for his guidance. And I want to thank you for your attention, and it will be my pleasure to answer any questions that you may have.
All right, thank you. And we can move on to the question and answer session now. So the first question, must the refractive index or relative refractive index of the nanoparticle or gel be known to accurately use DLS?
The refractive index does not have to be accurately known to use DLS, but we do need to know the viscosity of the solvent. So refractive index, no, but definitely the viscosity of the solvent because that will affect the diffusion coefficient.
Could you talk about how to select solvent for microgel characterization using DLS because it would affect the results, pH, ionic strength, size, and charges?
Sure. So in my lab, we had a cuvette-based dynamic light scattering instrument. And so what we would do is just simply suspend microgels in different buffer or solvent conditions and then go ahead and perform the measurement. That can take quite a long time, depending on the number of solvent conditions that you would like to screen for. And so if you're using dynamic light scattering as a screening tool, I really recommend trying to use the dynamic light scattering plate reader. Because then you can use or simply fill different wells with different buffer conditions, take a lot of measurements all in one swoop, and then know something about which buffer conditions have what kind of effect on your sample. In some cases, you may see aggregation of the sample, or you may see that the buffer or solvent is not appropriate for completely dissolving the sample, and so that will, of course, interfere with the measurement. But all of those things in combination can give you some idea of which buffer conditions are best.
What features of the light scattering data tell you that a polymer is branched versus linear?
Yeah, great question. So we do have branching analysis built into the software, and there are two ways you can go about this. One is if you simply plot the RMS radius versus the molar mass, and then look at the slope of the line that results, we can tell something about the branching behavior of the molecule. Alternatively, we can actually add a viscometer, an inline viscometer between the mols and RI detectors, and then we can measure the intrinsic viscosity of the sample. And when we do that, we then plot intrinsic viscosity versus molar mass, and this allows us to really dig down deep into the branching behavior of the molecule. We can tell you things like branching ratios, repeat units per thousand, which is long chain branching, and so we can really try to dig deep into what the particle looks like on the molecular level.
How do these techniques apply to hydrogels that are composed of individual molecules bound by non-covalent forces?
Yeah, that's a good question. So maybe you have some kind of hydrogel that just has physical entanglement, or it's connected in some other way. So pretty much the same principles would apply in terms of how you would analyze or go about analyzing these microgels or hydrogels. They would still, to my understanding, scatter light in basically the same way if they are a discrete particle. And it may be the case that trying to degrade those particles is actually a little bit tougher because, especially in the case of physical entanglement, that treating that hydrogel chemically is really not going to do much to break up that physical entanglement. But in terms of how you would go about the analysis of those particles, I think it would be just about the same. for measuring molecular weights and sizes and other factors.
Is it possible to do SLS with charged polymers?
Yes, absolutely, absolutely. The microgels that I talked about today were charged, and you can do that with pretty much any kind of charged polymer. So let's say you have a linear polyelectrolyte or something like that. It's certainly no problem to measure the molecular weight of that polyelectrolyte. And we can tell you, in many cases, whether that is behaving as some kind of extended conformation, or maybe whether it's acting as kind of a globular type of conformation.
Many swollen gels are optically clear. Does that interfere with the ability to perform scattering measurements?
It can. So if the refractive index of the sample is identical or very, very similar to the surrounding solvent, then the intensity of scattered light is going to be very low. So it definitely can affect the measurement. Now, something can have no UV response, for example, but that doesn't mean that it won't scatter light quite effectively. So we would have to know something about the individual sample there, I think, and be able to tell you whether we could get a good scattering signal from that sample.
Could you mention the name of the analysis software? Is it the same software that comes with all DLS machines from Wyatt?
Sure. So the DLS software is called Dynamics, and it is the exact same software that comes with all DLS instruments from Wyatt. That's exactly right. So the DLS software is Dynamics. The software that comes with static light scattering instruments is called Astra, and we have our own software team. They're constantly making improvements and changes to those programs. So be happy to share more detail about that if someone is interested.
Does the DLS plate reader tell if the polymer is linear or spherical?
So I guess the short answer is kind of. So if everything in solution is linear and kind of extended, then your hydrodynamic radius is going to be quite large. If the polymer is kind of globular in shape, then your hydrodynamic radius is going to be much smaller. Now, it may be difficult to tell just by looking at a single hydrodynamic radius number whether that polymer is behaving as in a linear fashion or a globular fashion. So it really would be useful to know, I think, both RG and RH, or test RH under different conditions to see if there's any kind of change in the conformation of the polymer. So in short answer is yes, but you need to know some more detail.
Can this technique be used for proteins, for example, predicting protein structure, folded or unfolded forms?
Yes, absolutely, absolutely. And so if we think back to the Nanostar, which is the cuvette-based DLS, it's particularly useful for looking at protein unfolding because it has that static light scattering detector built in. So if we track particle size or protein size over a range of temperatures, and we also track the molar mass over a range of temperatures, we can measure very small size changes, and we can also tell whether that change is due to an increase in molar mass, such as protein aggregation, or whether that size change is simply due to an unfolding event of the protein. So yes, DLS is extremely powerful for doing that type of analysis.
What prevents folding of the membrane with the larger particles? Is it controlled by concentration and flow rate? And do these requirements impose limits on the dynamic range?
Could you repeat that one time? I'm sorry.
Sure. What prevents the folding of the membrane with the larger particles? Is it controlled by concentration and flow rate? And do these requirements impose limits on the dynamic range?
Sure. Yes, there are different membranes available. I'm assuming we're referring to the membranes inside of the FFF instrument or separation channel. So if I'm answering this correctly, there are different membranes available with different molecular weight cutoffs, and that can have some effect on the separation of the nanoparticles. But probably what has a larger effect is the flow rates that you deal with. So you're exactly right. If you tune the flow rate and the cross flow conditions correctly, then you can get very fine separations between the particles. It does take some fine tuning. There are a lot of knobs that you can turn with FFF to get kind of the ideal method. So lots of things that you can change, lots of parameter space to explore with that type of analysis. But definitely membrane and cross flow and channel flow rates do have a large effect.
What is the maximum molecular weight and radius gyration that can be measured by SLS, and also the maximum hydrodynamic radius that can be measured by DLS?
Yeah, great question. So with static light scattering, the maximum molecular weight is somewhere around the 1 gigadalton range. And the maximum size for RMS radius is around 1 micron. So it's going to be, that range is going to encompass pretty much any nanoparticle that you can imagine. And in terms of DLS, the maximum size is going to be several microns. So I think we specify 5 microns for the Nanostar, and for the plate reader, potentially a little bit larger because of the scattering angle. So yes, I think that you can go up to pretty large molar masses and also pretty large sizes with those two types of techniques.
Can light scattering be used to characterize the underlying polymeric materials used to create microgels?
Yes, absolutely. There is a limit in terms of molecular weights that we can measure. So somewhere around the 200 Dalton range is the lower limit of molecular weights. So looking at just monomers may be kind of tough, but we can certainly look at microgels as they are forming into precursor particles and then larger particles and things like that. So we can definitely characterize the underlying materials that go into these microgels.
What limits the maximum size of the range for DLS measurements?
The main limitation is measuring the speed of diffusion of the sample. So on the small end, if something is too small, it's diffusing so quickly that the electronics cannot pick it up. On the high end, a large nanoparticle is going to be diffusing so slowly that it's, again, difficult for the electronics to pick up the diffusion of that particle in a reliable way. So There's also an influence of the angle at which we are measuring the scattered photons, but primarily it's limited by the diffusion speed and the electronics that are picking up the variation in light scattering intensity in the DLS instrument.
All right, that's all the time we have. Thank you again, Mark, for your fascinating presentation, and thank you to the participants for being a great audience. Be sure to check CNEN or CNEN online for information on the next edition of CNEN webinars. Thank you to On24 for technology and production services, and thank you Wyatt Technology for the sponsorship that made this interactive webcast possible. For CNEN webinars, I'm Alexandra Taylor. Goodbye. Hello everyone, welcome to today's webinar. I'm Alexandra Taylor, contributing editor for CNEN, and I will be moderating today's event. This webinar is titled, Well, Ain't That Swell? Characterizing Microgel Polymers and Nanostructures by Light Scattering, and is being sponsored by Wyatt Technology. CNEN works with sponsors to identify topics of interest and value to CNEN's audience and consistent with CNEN's mission to provide news and analysis of the chemistry